you very much for the invitation. So this is joint work really with quite a lot of different people, particularly Laura Curry, who's coming in a couple of weeks' time, and also Kumiko Hori in Japan, who some of you will know. Okay, so there's the obligatory picture of Jupiter with its dark horizontal belts. And there's the great red spot. Let's see if this works. Oh, yes, very nicely in the southern hemisphere. And of course, these belts and zones are associated with strong east-west flows. And the picture looks like that. So that's what the surface zonal winds of Jupiter actually look like. I'll just go through a little bit about this. There's a strong equatorial belt here, which is eastward. I think Jeff is going to be telling us why it's eastward rather than westward on Thursday. There's a strong belt, jet up here, which is about 21 degrees north. And there's the great red spot, oops, yes, sorry. The great red spot over here, which is rather disrupting the picture. And you can see it's really quite asymmetric about the equator, and that turned out to be quite important in this story. And probable reason for the asymmetry is the presence of this great red spot in the southern hemisphere with no equivalent thing in the northern hemisphere. So we're talking in terms of cylindrical polars, S phi Z and R theta phi. So theta is the co-latitude. I won't say any more about that. Okay, so how do we actually explore what's going on in Jupiter's interior? So unlike quite a lot of the talks you've been hearing about, I'm going to be focusing on not what actually drives the winds or why the winds have the form they do at the surface. I'm going to be concentrating here on the question of how do they vary as you go into the interior of the planet, and why do they do what they do? So that's basically the focus of this particular talk. So it's slightly different from a number of the other ones that you'll be hearing. So when we're looking at the interior of Jupiter, there are three main ways of actually getting information out. One of them is to look at infrared observations. There's a Juno infrared camera. Juno is the mission which is going around Jupiter. It landed got to Jupiter in 2016, and so it's done nearly 8 years now. And it's produced a huge amount of data back, and it's nearly all that data is what I'm going to be talking about here. So this infrared signal comes from below the surface layers, so it tells you a bit about what's happening deep down, but it only goes to about 50 to 100 kilometers below the 1 bar surface. And we don't really know exactly where it's coming from, to be honest. But it nevertheless is definitely telling us about stuff in the deeper interior than you see at the surface. The other main method is to measure Jupiter's gravity field very accurately. Because Juno gets very close to Jupiter's surface, it can do this incredibly accurately. So the gravity field of Jupiter is now known to an amazing degree of accuracy compared with what it was before Juno actually arrived. And you can, the Cassini mission, which was earlier, did pass close to Saturn, so you can do the same sort of job for Saturn as well. So what we actually learn from this is the gravity field, that's the gravitational potential, and it's expanded in spherical harmonics, and the coefficients of those spherical harmonics give you the information that you want. And we now know about what this number is for n up to about 30, which is pretty good, actually. The non-axis symmetric components, the one with the non-zero m, tell us about the tidal response, and that's very interesting too, but I'm not going to be talking about that. I'm going to be talking about the axis symmetric components, the m equals 0 components, which are the zonal components, which give information about the zonal flow. and the information is coming from about 2,000, 3,500 kilometers deep. And the third weapon in our arsenal for understanding what's going on inside Jupiter is the magnetic field. And the magnetic field is actually changing. One of the very fortunate things about the Juno mission is it was originally planned to go in a pretty circular orbit, which would have gone around about once a day. And the whole mission then would have only lasted about 1 year. Fortunately, one of the rockets didn't fire, with the result that the thing is in a very elliptical orbit. It takes something like 50 days to go around, actually to get close to Jupiter, and then it goes a long way away and then it comes back. But the huge advantage of that is that it means that it's sort of safe when it's not close to the radiation belts of Jupiter. So it's actually lasted for 8 years. So we've actually got far more data as a function of time than we ever thought we were going to get, which is extremely nice. Because Jupiter's magnetic field is not actually constant, it's actually changing, and it changes because of flows inside Jupiter itself. So by watching the changes in the magnetic field, you get some idea of what the flows are deep down. And those signals probably come from about 3,500 to 7,000 kilometers deep in the interior of Jupiter. I should say that Jupiter's 70,000 kilometers deep, so that's a nice easy number to remember. So 3,500 is 5% into the interior. Right. Okay. So the gravity coefficients of Jupiter are actually determined essentially by the density perturbations. So although they're small, of course, they're definitely non-zero. The antisymmetric components. The antisymmetric components must come from the zonal flow. If the Jupiter was rotating homogeneously like a solid body, then of course it would be oblate. There would be even coefficients in the gravity field, but there would be no odd coefficients. And the odd coefficients come about because the zonal flow is asymmetric across the equator. So that's actually quite important. So the great red spot produces this asymmetry is helping us a lot here. However, now actually in the latest data, it's now the gravity field is known so accurately that even the coefficients up to degree 30 are known. And those higher order ones, up to even the even ones there, are all caused by the zonal flow rather than the gravity model. So, yep. Yes, the J is the spherical harmonic coefficient, yeah. So the big one, I mean, J2 is a big one because that measures the oblateness. J4 and J6 are pretty big because they're all to do with the basic structure, the fact that it's not a spherical object. And the odd ones are all due to the fact that the centrifugal force pushes the fluid out in some places more at the top and less down here, and that produces an asymmetric Jn. That makes the asymmetric density, and that produces the asymmetric gravity field. So what we do is we can write down an equilibrium model of Jupiter, a rho bar, and then there's a rho prime, which is the perturbation due to the rotation, due to the zonal flow. Sorry, not due to the rotation, due to the zonal flow. This one here actually has the uniform rotation part in it, and then that gives you the combination of rho, and then you look at Poisson's equation, and you get a relationship between the gravity field, which is observed, and the density perturbation. That then tells you basically what the change in the Jn coefficients is from the zonal wind. You then look at the perturbed equation of motion, and then you take the phi component of the curve of that equation of motion, which is basically a thermal wind type equation. And that tells you a relationship between the d by dz of the rho bar u and d rho prime by d theta. So basically what you do is you make a guess as to what u is, You then work out rho prime from this equation and v prime from this equation. You put it into here, and then you get a change in the gravity coefficients. And the first time you do that, you get the wrong answer. But then you keep adjusting your zonal flow until all these numbers, delta Jn, actually agree with the observations. And then that tells you basically some information about what the structure of the zonal flow actually is in the deep interior. Now, because of this rho bar term here, if the zonal flow close to the surface doesn't really come into this very much, because that's close to the surface, the rho bar is rather small, so this term is pretty small anyway. Deep down, everything is more or less moving homogeneously because the magnetic field locks the whole thing together. So deep down, there isn't much of a signal. So it turns out that most of the signal is coming from that 2,000 to 3,500 kilometer range, which I mentioned earlier. So now the question is, what do you get for the zonal flow? And the way this has been analyzed is to look at basically a geostrophic type zonal flow. So the first idea is that the flow is perhaps completely geostrophic. So what you see at the surface can be continued down in the z-axis right down into the interior. Now, obviously, that's not right, because it would be impossible to have it it would all be completely symmetric if that was the case, and we know it's not. So clearly there is a change. There is a change as you go down with depth. So what we actually do is, this is a decay function, which is a function of r, and we multiply this geostrophic flow by this decay function, which is a function of r. And obviously you choose QR surface to be 1 because it's got to match up to the observed zonal flow at the surface. And that gives you then a pattern. But when you actually compare with the gravity data, the decay function that you actually need is like that red curve there. Don't worry about the gray ones. They're all things from individual coefficients. This is the one which is the integrated thing over all the coefficients. So that's the one with all the data in. And you can see that it goes down from the surface at 1, of course. It drops out pretty monotonically and smoothly, remarkably so, actually, down to fairly low values, well, down to about 3,000 or 4,000 kilometers. So it's got really quite small down here, this decay function. So that is basically what you get out. So the result from the gravity data is basically this picture. If you actually look at what this looks like as actual flow in Jupiter, this is the surface of Jupiter. That's the 1 bar surface of Jupiter. That dashed line is 3,500 kilometers below the surface. These contours here are what that whole zonal flow, that's the U0 of S times the decay function Q of R, that's what it actually looks like. And you can see here that it is fairly aligned with Z. It's certainly highly rotationally influenced. If you tried to fit this gravity data to, if you tried to fit this gravity data to something which was decaying purely as a function of R, if you didn't have that S dependence in it, if you tried to fit the surface to something purely with R, it's completely hopeless. I mean, it's just totally not consistent with the gravity data at all. So basically, you have to have these zonal flows are going on a sort of almost quasi-geostrophic way as they go down, but we have this decay function, so they are actually dropping off as they go into the interior. So you can also see actually that the signal comes mainly from the deep jets at latitude 20. Those are the ones that are actually going deep down, and it's stuff here which is really perturbing the gravity field a lot. This stuff actually near this, although the central jet is big and fast, the equatorial jet is big and fast, it doesn't actually go very deep at all. So it doesn't actually do much to the gravity signal. So what you're actually detecting is basically these jets here and these jets here. As you go further up, the jets get weaker and weaker, and they don't go down very much either. So the whole signal is really coming from this bit and these bits down here. Right, okay. So let's think a bit about that. So how can it be that the thing is not completely geostrophic? Well, again, if we look at the thermal wind equation, not quite the same as the one that Caspian, the people from Weizmann actually use. This one is the divide by R first and then take the curl and the phi component. This then tells you that the rate of change du by dz, so that's the ageostrophic part of the zonal flow, the changing part as you go deep down, that has to be caused either by a thermal wind. It's actually an entropy wind, really, because this is the S prime is the entropy gradient. Of course, it's a highly compressible atmosphere here. So it's that's the latitudinal variation of that. If you go into the deep interior, the Lorentz forces could be doing things. The viscous forces are probably pretty unimportant anyway. So it's basically these terms which are the major players. Now, this one here was thought originally that this was going to be a very important term in this equation. But actually, by the time you get down to 3,500 kilometers below the surface, the conductivity, the electrical conductivity is not that large. And the consequence of all that is that the magnetic field actually doesn't do all that much to the flows to this equation. The main balance in this term is between this term and this term. This was actually a bit of a surprise. The history of this subject is quite amusing, really. There were a whole, before we knew anything about the gravity field and Jupiter, there were a whole lot of people who thought the jets were extremely shallow, yes, and they thought it was all up in the upper turbulent atmosphere, and that as soon as you got into the interior, there would be no wind at all. Basically, it would go down to zero rather quickly. Well, that turned out to be totally wrong, of course, because we now know that they're going down at least 3,000 kilometers. There were other people like me who thought it was deep. So in a sense, we were right, but we weren't really right, because what I thought was that it went down to where it's cut off by the magnetic field at the bottom. So I was expecting the zonal flows to go about 7,000 kilometers deep. Jupiter, of course, always likes to play jokes. I think that's one of his features in mythology. So needless to say, he arranged things so that we were all wrong. And actually, it cuts off much lower down. I mean, the reason why I didn't think that this term was going to be all that important, we'll come to that later, but the fluctuations in entropy, which actually drive convection, are extremely small. They correspond to something like 10 to the minus 4 of a degree centigrade. And that's all you need in order to actually get the heat out of Jupiter by convection. And in order for that term to balance that, you need something which corresponds to about 1 degree centigrade entropy difference. 10 to the 4 times bigger than I was expecting, or what actually would drive the convection. So that's the problem that we're facing, really. Why is this term so big, and why does this one actually bring the zonal flow basically down to zero, but the zonal jets down to zero long before this one actually gets into the scene, into action? Okay, so that just says what I've said before. Okay, so that's the only possible player, really, is that variations of 1 degree over the jet space. And well, I mean, It doesn't sound a lot when you only say it's 1 degree, but it doesn't seem much. But as you say, it is 10 to the 4 times the temperature fluctuations that are driving the convection. Now, there are two ideas about where these large variations could come from. There's the one which I'm going to put forward to you today, which is that they come from essentially from the stably stratified layer, which is near the surface, which is known and is observed. But it's also possible that there could be a stably stratified zone lower down. And Christensen et al. Produced a model of that. And there's quite a lot of work being done on this model now. And both of these can lead to significant du by dz's. They both have a meridional circulation being driven. So the two ideas are quite similar in some sense. I mean, we're both thinking that the origin of these large temperature fluctuations is coming from some sort of stably stratified layer. It's just that we're not quite sure at the moment where that stably stratified layer is and which layer it is. So I'm working with Laura, and we're looking at the surface one to see how the flow varies with depth on that basis. Now, giant planet zonal flows can be mainly driven by the surface. Because of the thing being sort of fairly geostrophic or quasi-geostrophic, when you push things, it could be pushed at the top and then the whole column move, or it could be pushed at the bottom and the whole columns would move. So you don't a priori know exactly where that forcing is actually occurring. The only thing you know is that there's an integrated forcing all over the whole column, basically. Right, okay. Yeah. So let's have a look at this model now. So this is a very simple model. We've simplified things with a Boussinesque fluid here. We've got convection, rotating convection going on inside here. We've got gravity and rotation parallel. We have looked at the angle case, which is, of course, more realistic for the geometry of the spherical geometry of Jupiter. But it turns out that this actually gives you quite a good idea of what the key dynamics is, and it's much simpler. So we've stuck with this one for the time being. We force the flow by moving the boundaries. So the first model we have is a no-slip boundary. And at the top here, instead of having a stationary boundary, we've got a boundary which has got a sinusoidal variation. So it's got the eastward and the westward jets all imposed. So we're not here addressing the question of why these Reynolds stresses drive the things. We're assuming, yep, the Reynolds stresses do their job and it drives them in this fashion. And what we're trying to look at is now, is how it varies with depth. Okay. Now, sometimes we'll have a stably stratified layer, and when we did, so it's all, we want just the top bit to be stably stratified. So this curve here gives you dt by dz. That's the rate of variation of temperature with height. That's the stable stratification near the top, which is known. And this isn't exactly what it looks like. It's much more complicated, but it is known. And we could put in a much more realistic stably stratified layer. So this is actually known. Right. So these are basically the equations. So just to see what we're actually doing, we're solving convection, usual rotating convection in the sort of standard sort of thing. I don't think I need to go through this in much detail. I just flash this up, show it so you know basically what we're doing. This dt by dz here is where the stable stratification term comes in, the Taylor number, Rayleigh number, and Prandtl number. And of course, we want to write down the thermal wind equation here, which comes from taking the curl of the equation of motion, and it's the y component. So we've got x is the zonal direction, so x is the longitudinal direction, y is the latitudinal direction, and z is the radial direction, so that's the vertical direction here. So make sure I know what the geometry is. Okay, so the very first things we tried were no stratification, no stable layer at all, just to see what the effect of putting this zonal flow actually at the top is, i.e. driving the zonal flow through the boundary. What does that actually do? And the thing it does is it produces a zonal wind, which goes from quite high values there where it's being forced there's a boundary layer here, which is basically an Ekman layer here. And because we've got it fixed to 0 at the bottom, there's another one down here. And the flow is fairly flat in here. It's fairly geostrophic, but there is a slight slope here, which we'll discuss as to where that comes from in a minute. But the most immediate observation is that it's absolutely totally different from the picture that we got in from the data. I'll just flip back quickly to the picture we got from the data, because you do need to remember that. The picture we got from the data was just a smooth drop from here, no particular boundary layers, just a smooth drop down all the way from the top to the bottom. What are we getting from this model? We are getting something that actually slopes the wrong way and is mostly dominated by the boundary layers. Now, you might say, oh, well, of course, that's going to happen because you've got Ekman layers, because you've got artificial boundaries, no slip boundaries. Jupiter doesn't have anything like that. But actually, if you replace that simple forcing of moving the boundary by an imposed zonal flow, in other words, you drive the zonal flow with a forcing, which of course you can do by adding a term into the equation of motion, that will then produce a flow which is more or less the same as this at the top, and that actually behaves in exactly the same way. You still end up with this thing going the wrong way, even though you've got a stress-free boundary. So it's not the stress-free boundary which is producing this thing going wrong. It's the nature of the Ekman suction, or the suction that's produced by the Reynolds stresses. So let's have a look now. Well, this explains it in a bit more detail. So why is it going the way it's going? Well, if there's no stable layer, dt by dz is negative everywhere because it's unstably stratified. So it's hotter at the bottom and cooler at the top. And the place where the Ekman suction comes, where the Reynolds stresses are actually driving the flow up and down, in this picture here, it's at basically at y=1 latitude here, and yeah, it's y=1 latitude here, and sorry, yeah, okay, I haven't got the picture here, but it's sucking it down here and pushing it up here. Okay, so that is then combined with this temperature gradient here. That is actually what is producing that temperature picture there. That is what is making it hotter here and cooler there. Okay, now whatever you do, the suction is always linked with the vorticity pattern that's coming from the zonal flow, and you can't do much about that because we know what it is, it's measured and it's observed. So the only thing you can really do to change that picture around is to change the dt by dz. The dt by dz, the stable stratification term. Okay. So this is what we're doing here. So now we're going to actually change the dt by dz. So we've got the stably stratified layer in, and you see it turns it around completely. Now the hot bit now is at y=3. And the cold bit is up here. That's because we're sucking down relatively warm fluid from the surface from the stably stratified layer. And so that is actually much hotter now than that. That has turned around this thermal wind with the result that it's now looking much, much more like the Jupiter pattern. It's still not really right. I mean, it's still got boundary layers. We're hoping that when we get the model more accurate, taking things like the variation in density, I mean, this is a Boussinesq model, so you wouldn't expect it to be pretty accurate, quantitatively accurate, but we think it is sort of qualitatively doing what we want it to do. So the thermal wind balance is now leading to a more gradual reduction of the zonal winds with depth, more or less as happens in Jupiter. Now, obviously, this suction in this meridional circulation, you can ask yourself, well, that's fine in all the theoretical models, does it really happen in Jupiter? And the answer is apparently yes. This paper here is an observational paper from these guys in 2021. And they looked at the infrared signal, which is coming from that region about 50 to 100 kilometers below the surface. And they infer from that there is indeed what they call feral cells. So feral cells are basically axisymmetric meridional circulations which turn over and occur on the in the Earth's atmosphere. I mean, Ferrel was the guy who picked these things up some 100 years ago, I think, in the Earth's atmosphere, and the same name is being used in Jupiter's atmosphere. But of course, these feral cells are only on the same length scale as the jets are. And since the jets go backwards and forwards, they're on a comparatively short length scale. The feral cells on Earth are much larger structures. There are only a few of them. There are loads of these things in Jupiter. So, I mean, what are these things? These things are driven by the Reynolds stresses, and they balance basically the Coriolis term here. So that produces the Reynolds stresses then produce a V bar. And of course, if it produces a V bar by continuity, since it's axisymmetric, it's obviously got to produce a W. So it's got to go round, and it's got to actually suck material up, and it's got to take material down. So these circulations do actually seem to be happening in Jupiter. What we don't know actually is how deep this actually is. There's some discussion in this paper, but the bottom line is it could be just 100 kilometers deep, or it could be thousands of kilometers deep. There's no way we can actually tell that from observations yet. Okay, so what controls the depth of the zonal flow? Well, what I think may be going on is this. Even if the feral cells are relatively shallow, I think they are setting up the horizontal temperature variation across the cells. So they are producing this 1 to 2 degrees K lateral variation. So if we go back to this picture, these feral cells are producing this type of variation at the top. Once that's happened, even if the feral cells don't actually extend into the deep interior, then what is going to happen is basically we're going to have a turbulent diffusion, and that turbulent diffusion equation is going to be taking that temperature anomaly at the surface, and it's going to be evening out. And the length scale over which it's going to be evening out is going to be comparable to the length scale over which it's imposed at the top. I'm basically, in a really crude way, you're just solving del squared T equals 0 with the temperature perturbation given a sinusoidal perturbation at the top, and you're asking how deep does it actually go? Now that, of course, is a super crude model, but I think it's giving you the idea that produces a vertical length. And because the horizontal scale is a few thousand kilometers, the vertical scale is going to be that too. So it's going to be, it could potentially produce the right answer. I'm not saying for a moment that it does produce the right answer, because the models to date are really rather oversimplified and so on, and we don't really know it in detail. But all I'd claim at the moment is it's a promising idea, which actually could be working. So, of course, when you solve del squared T equals 0, you're assuming that the diffusion coefficients are all isotropic. Now, it is extremely unlikely in rotating convection that the diffusion coefficients are isotropic, because we all know that in rapidly rotating convection, you get tall, thin columns. The length scale, the horizontal length scale, is quite different from the vertical length scale. So it's a lot more complicated than that. So in a sense, when I say it is just governed by the diffusion equation, I'm sweeping an enormous amount of complicated analysis under the carpet there. We don't actually even know really whether the primary source of turbulence is actually the convection down there, or it could be due to the baroclinic instabilities, because the jets, of course, have these horizontal temperature gradients, we could expect baroclinic instabilities occurring. So the baroclinic instabilities could be leading to turbulence. It may even be that it's not necessarily rotational turbulence, which is actually driving the yes, that's exactly, that's what I'm really saying. That's exactly what I'm saying. I'm saying that even if the convection was pretty negligible, say, you'd still expect the turbulence to be there because you're just, I mean, these are shearing motions, and therefore they're quite likely to be turbulent. So that's one of the issues we just don't know at the moment, is exactly what the nature of this turbulence really is. And that's a really interesting question, I think, actually. So we're hoping to do some more on this, of course. So basically, my picture is that this turbulent diffusion, however it works, is carrying this surface temperature anomaly down to about 3,500 kilometers, between about 3,500 kilometers to 7,000 kilometers. I think the thing is probably pretty geostrophic and probably pretty small, the zonal flows. And the fact that it's all set down to basically zero, down to 7,000 kilometers, that's because that's where the magnetic field is actually locking everything together. So, of course, without the magnetic field, there'd be no reason for it to be locked together or go down to zero at all. But because the magnetic field is there, that's essentially what is setting the bottom boundary. So the original ideas weren't completely crazy, but they weren't actually quite right either. Okay, so there we are. Right, so I'll just move on now. So that's basically the conclusion there, and I think I've said all that actually now, so I don't think I need to stop there too much. Okay, so the relatively large horizontal temperature, that's important. The ferrule cells are important, and the depth of the zonal wind probably being maintained against turbulent diffusion. That's crucial too. Okay. So now I want to talk about another topic a bit, fairly briefly this time, but it's all connected with what I've been saying, and that's the magnetic field. I mentioned that Juno has produced a lot of new data. It's produced fantastic measurements of Jupiter's magnetic field. We knew hardly anything. It was thought to be basically dipolar before. Well, it's a lot more complicated than that. The field actually comes out more or less near the pole, slightly off center, but that's like the Earth's one. What's completely different in Jupiter from the Earth is that it re-enters actually quite near the equator. This thing has been called the Great Blue Spot. That's because it looks blue in these pictures. There's no magnetic fields, don't have any particular color. Mind you, come to that, actually, the planets themselves, the colors that you actually see in those lovely pictures of Neptune and Uranus and so on are all highly artificial anyway. So really, it's just as much a great blue spot as anything else. The great red spot isn't particularly red either, come to that. So anyway, this is known as the Great Blue Spot, and it's where the magnetic field re-enters, having come out from there, Jupiter. And I mentioned that because Juno's lasted a long time, we now can see the differences. Well, you look at that picture and you look at that picture and you say, what difference? They look pretty similar. Of course, the secular variation, the actual change from wherever it is, that's 2017 to 2019, is pretty small, but it's non-zero. So this is what's happened, and most of the signal actually is around this great blue spot, and it's moving eastward with time, which is why this bit is bluer and that bit is redder when you measure the time derivative. Yeah, that's basically that's the JRM33 model minus the earlier JRM09 model. So what's happened is that the Great Blue Spot moved eastward by about 2,200 kilometers. At least that's what we thought 3 years ago. And that would correspond to an eastward drift of about 4 centimeters a second. Now, remember, the zonal flows are 100 meters a second. we're now down by a factor of 10 to the 4. We're now talking about centimeters a second. That's the extent to which all that zonal flow is actually dropped off by these sort of depths. I think that's probably due to the effect of turbulent diffusion, which is brought it right down from the high values down to the low values. But it's actually quite a bit bigger than the Earth's sub-secular variation. The Earth's westward drift of the field is about 0.05 centimeters a second, so a lot smaller. However, fairly recently, a few years ago now, I guess, it was noticed that that 4 centimeters a second figure is actually not really correct, and it's been revised down to about 1 centimeter per second. Basically, what was wrong with the 4 centimeters a second is that the rotation period of Jupiter wasn't actually exactly right. It was nearly right. It's 9 hours, 50 minutes, point something, 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 but it's the point something, something, something that was wrong. So it's now being corrected. So we now know what Jupiter's rotation rate really is. And when you do that, you see that quite a bit of this eastward drift of the great blue spot was actually due to the fact that we had the rotation rate wrong. But it's still moving. It's been revised down to about 1 centimeter a second, but it's still, as you can see from this picture here, the velocity, they have to measure something called the flux velocity, which I'm not going to go into, but basically the velocity of that patch is still moving at about 1 centimeter a second. Now, even more interestingly, from my point of view anyway, is that recent evidence suggests that that velocity is actually slowing down. Now got, this is up to 2019 picture. They've now got the picture right up to 2022. I mean, it takes a few years for it to all get sorted out. It will go to even further because it's going to go on to about 2025, the thing. So there will be more data coming out recently. And it looks like that velocity is slowing down. So, I mean, the simplest picture of what's actually happening here is that you've got a lump of flux, the great blue spot. The flow is moving along, it's carrying that flux along with it, and it's advecting along at 1 centimeter a second, except that it isn't because it's actually slowing down as a function of time. So what that would suggest is that what we've actually got is an oscillation. It's going to come back. It may even come right back and go the other way. It may end up going westward after having gone eastward. So that's what we think may be happening here. And now these things are called torsional oscillations when the whole fluid moves one way and moves backwards. These things are known in the Earth, so it's not complete fantasy that this thing could happen in Jupiter. The ones on the Earth, in the Earth's core, are about 6 years, and we see them in 2 ways. We see the actual changes in the magnetic field, just as we're seeing the changes in the magnetic field in Jupiter. In the Earth, you actually measure the length of the day, because if a chunk of fluid in the core is going that way, in order to preserve angular momentum, the mantle has to be going the other way. And if the mantle's going the other way, that means that the rate of rotation, the mantle, which is where we sit on and our clocks are all measuring, that is actually slowing down. So actually that torsional oscillation produces a change in the length of day. Only milliseconds, of course, but nevertheless, it's measurable. Yeah. Yeah, there is. Yeah, there is. In the sense that, I mean, as the thing moves out, it stretches the magnetic field a little bit, and then it moves back. But the answer to your question really is basically no, because the basic state magnetic field is not going to change all that much. So it's only really the little changes and the currents associated with them, which are really important in this torsional oscillation. I mean, these things are all, we're talking about centimeters a second. They're pretty small things here we're talking about, really. So it's not really going to, it's going to change the magnetic field a little bit over these time scales, but not a huge amount. So that's a picture of what a torsional oscillation looks like. So that's a cylinder of fluid moving that way. That's a cylinder of fluid moving that way. It's coupled by the magnetic field, so that the tension forces in the magnetic field pull the thing backwards and forwards. So you could sort of see how it's going to work from that picture. And the period of these things is years. So as I said, the planetary vorticity is huge, so the inertial wave frequencies are hours rather than years. So these are much weaker forces, but they still are potentially observable. And these torsional waves, they can propagate either outwards, like that, or inwards, of course, depending on how it's forced. And the torsional oscillations are the standing waves associated with that. Right, so I've written down the torsional wave equation here, just to give you a flavor of what the torsional waves actually are. And you can see here that there's this UA squared here, which is the alphane speeds basically squared here. And that is dependent on BS. So it's important that it's the radial component, the cylindrical radial component of the magnetic field, which is actually doing this, because it's that which is coupling the cylinders together. Now, we think probably the driving is from the Reynolds stresses, and those are probably near the surface. But how deep the forcing goes is uncertain. Yeah, it's not at all agreed by everybody, but we have a picture, but not everybody agrees with it. Okay, so yeah, so that goes there. So now what we do is we look at the magnetic field of Jupiter. Now that's the static, that's the mean magnetic field. So that comes back to your question. We're imposing that in order to calculate this frequency. And we calculate it by evaluating what BS is over these cylinders. And actually, one of the surprising things is, we did do this way before any of this actually came up. Kumiko Hori took a Jupiter model that I had, and she looked for torsional oscillations in there, and we found torsional oscillations. But because we didn't know what the real magnetic field of Jupiter was like, we couldn't actually calculate the frequency of this thing with any degree of certainty at all. And we got a value which was actually much too long. The reason is because this great blue spot actually has quite a big influence, because it produces a whole lot of sort of cylindrical field, which radial field coming out near the equator, which is completely unexpected. I mean, if the field had been dipolar, a dipolar field near the equator is pretty well all in the Z direction, not in the S direction. But actually, Jupiter's field has a whole lot in the S direction. So that speeds the whole thing up again. And that's why these things have got the frequency they have. Okay, so we measured what the frequency, we measured the alphane speed first of all. Then to convert that into a period, you need to know where the forcing is coming from. Well, if the forcing is coming from the surface winds, then that's quite convenient, because then that gives you a wavelength in the S direction. So you can then twice the interjet spacing, about 6,000 kilometers in S is the wavelength of these things, and that tells you that the torsional oscillation period comes out to be about 10 years. Again, I mean, that choice of wavelength comes from the fact that we believe it's being driven by the surface. Not everybody agrees with that. In fact, Jeremy Blockson sort of thinks that it may be being driven actually by flows in the deep interior, and that is possible too. So if that's the case, then his length scale will be different from ours. So he would get a different time scale. But anyway, that's where we are at the moment. Now with the 10-year thing here, as in the solar cycle, a 22-year cycle usually gives you an 11-year signal, of course, the famous 11-year period. So we'd expect the torsional waves here to give an observational signal on a period about half that, which is about 5 years. And we were quite excited by this because this is a picture of what the forcing is looking like at the surface, because that's the variability of the zonal flows. They are more or less fairly static on a large scale, 100 meters a second there. But they do vary in strength, particularly actually in this sort of 21 degrees north one here. Yeah, and they can vary by about sort of 10 meters a second. So there are a few percent variations in the strength of the zonal winds. So if they're varying over a 5-year period, then that could provide the forcing, which is actually setting these torsional oscillations in motion. Yeah.
Planetographic planetary.
Oh, yes. Yeah. Now that, no, they're not. If it's a perfect sphere, yes, they would be the same. Very annoyingly, the observers all measure planetographic latitude because that's the slope of the surface, you see, and when you look through the telescopes, that's the thing they easily measure, is the slope of the surface. What we work in terms of the planetocentric coordinates, which is a sort of mathematician's coordinate system where the origin is in the middle and it goes radially out. And they're not exactly the same because Jupiter is oblate. Yes, now that's the sort of thing that gets you confused right at the beginning of this topic. There are lots of little things that the observers do which are slightly non-intuitive because of the way because of the way its history is developed. So yeah, so the one that I'm particularly interested in is this North Tropical Belt oscillation here from that big zonal jet there, and that had a period just about 5 years. So these periods here are now seen not in the torsional wave data. These periods are being detected in the infrared radiation. So these are from ground-based observations. Ground-based observations have been looking at the infrared radiation that's coming out of Jupiter for a long time now, since previous century, actually. And so that's a long enough period to actually start doing proper periodograms of the data. And they do find periodic behavior in that. And, well, surprisingly to me, the periods that they're getting are all comparable with this torsional oscillation period. Now, we all know that just because the periods are the same as the data doesn't necessarily mean those two phenomena are connected. But nevertheless, I mean, they could be, exactly, they could be. And that's basically where I came in. I mean, I sort of started off by being quite amazed that the numbers came out to be the same. So I was sort of terribly buoyant about the whole idea. Then I sort of thought of it, how on earth are these oscillations of a few centimeters a second, how on earth are they actually controlling the heat coming out of the surface of a huge planet like that? Oh, well, it can't, it must be a coincidence. And then the data about the torsional oscillations from the secular variation came in, and then I was like, oh my goodness, these torsional waves, they really do exist. They're really there. So then I got to sort of, you know how it goes in these things. Oh my goodness, perhaps this idea is really right. But I mean, we'll find out in the course of time as to how the data actually evolves in time. But it is an interesting coincidence, if you like, that that period is actually the same. So then, yeah, so those are the periodograms that the observers have produced, and you can see these sort of bright spots. This one here, the 2 and the 3 are the ones that I'm particularly interested in for the torsional oscillations. There are some of the periods close to the equator which don't really fit with the idea quite as well. But again, I mean, again, it's all a question of exactly how what's going on in the deep interior connects, of course, to what's going out near the surface. We don't really know that. In my attempt to explain how there could be a causal connection between these things, I looked at, basically my problem is that these torsional oscillations are only a few centimeters or maybe even 1 centimeter a second in amplitude. So, but can that actually affect the heat flux coming out of the planet? It is possible. I mean, the turbulent velocities actually near the surface are very high. There's loads of turbulence actually near the surface. There's loads of convection coming up from below, and these things are bringing up huge sort of thunderstorms and lightning and God knows what, actually at the surface. But if you go down into the interior, the theory of rotating convection, whichever one you believe, I mean, there are various formulae in the literature. This is not a fully understood problem. But all of them basically have a row at the bottom here when they are constructing the velocities. And because the density is very small at the top and very big as you go interior, that makes a huge difference. So although the velocities are going to be big where the density is small, you go into the interior and all that heat flux can be carried out with really not a very big velocity at all. So the actual convective velocities down in the interior could be of the order of a centimeter a second. And if that is the case, if the shear being imposed, I mean, if you've got shears being imposed of the same sort of order of magnitude as the velocity is actually turning over, then it is possible that the heat flux could be actually affected by this torsional oscillation. So that's my positive spin on it. So I think because, but of course that means that the whole action has to be happening deep down. If that idea is right, it means that the blockage basically being produced by the torsional oscillation must be occurring actually something like 1,000 kilometers or more down below the surface. Okay, well, it's nearly lunchtime now, isn't it? So I think we seem to have got to be 29/30. So that's the conclusion on, that's my optimistic conclusion on torsional oscillations. So waves travel about 2 centimeters a second. They could be driven by fluctuations enforced by the turbulence of the surface. They could, as Jeremy thinks, actually, they could be driven by similar fluctuations going on in the deep interior. Of course, that's possible too. They may be the source of the periodicities of the traveling waves seen in the 5 micron radiation signal, which has been detected from Mauna Kea. That's the Hawaii telescope. And I think also now seen in Juno data too. So the amplitude of the oscillations are probably only a few centimeters a second at the most, pretty uncertain, of course. And the secular variation constrains the amplitude and is sort of consistent with that sort of number. And the 5 micron signal could be the result of torsional oscillation shear flow impacting on the convection. And that would also give you a 5-year period compared with the 10-year of the whole magnetic oscillation. So it'd be like, it would give half a period like the sunspots do. Okay, and there's a bit about the stably stratified layer there, and well, I'm not going to talk about that, but I mean, there may be stably stratified layers, as Uli Christensen and his team have thought, and that would affect the nature of the torsional oscillation as well. I mean, that could actually change the picture. It slightly complicates that torsional oscillation. It's still basically the same, but it's no longer completely geostrophic. It's that they then can, the torsional waves can actually vary with Z. Okay, well, that looks like a good place to stop. Okay, and we seem to have got to lunchtime, which is always good. Okay.
What's your view on the mechanism of production of the stable layer?
Oh, production of stable layer near the surface. Oh, I mean, that's due to radiation, isn't it? I mean, the heat is coming near the in the interior. It's all basically has to be by diffusion, yeah, because the opacity is quite high down there. So the radiation has to leak out basically by diffusion. Once you get near the surface, then there's radiative transfer, and the radiative transfer can cool the whole thing down and bring it into almost isothermal, well, to bring it towards an isothermal behavior, so that instead of being close to adiabatic, which is pretty well got to be in the interior, when you get to near the surface, because of the radiative transfer, then the temperature gradient will start to move towards an isothermal type pattern. And then, of course, that implies stably stratified. Oh, well, that's possible too. It's possible too. I mean, I'm sticking to what I might call the simple explanation here. I mean, it could be. I mean, it could be. I mean, the chemistry, of course, is complicated, and stable layers can be caused by the chemistry.
The radiation lies more in Jupiter's stratosphere.
Yeah, well, yeah, but it brings it down to it does bring it down. I mean, the models that people have. I mean, I was looking at that Marcus model recently, and they have it more or less stably stratified down to about 50 to 100 kilometers below the 1 bar level. I mean, that's sort of. But I mean, you're right in the sense that we don't really fully understand it. I mean, Uli Christensen, I mean, when we're talking with him, we always say, oh, well, you've got this stable layer at 3,000 kilometers depth. That's about the only place where the theory says there's no stably stratified layer pretty well. But he would say that we don't understand the chemistry of Jupiter's deep interior. So we don't really know whether there could be a stable layer down there. I mean, complications of the chemistry could do all sorts of things down there that we don't currently understand. Yeah. Yep.
Does a turbulent magnetic diffusivity ever get in?
Not really, no, because at about above 3,500, the molecular diffusivity is quite large. So you don't really need to go to turbulent diffusivity. If you go deeper, then the magnetic Reynolds number starts to get big. And then, of course, yeah, you will. And indeed, yeah, it's a very interesting question, is that actually, I mean, the models, we run the models always with magnetic Reynolds numbers 1,000 at the maximum, because you can't do the numerics with higher. I mean, we know that if you calculate the magnetic Reynolds number down there on molecular basis, it will be millions rather than thousands. But we sort of argue that it looks reasonable because there's probably enhanced diffusion coming from turbulent magnetic diffusion. I mean, yeah. Mm. Yeah, that is definitely a good point, actually. That is definitely a good point. Yeah.
Almost impossible to detect toroidal magnetic field.
Yeah.
But numerics.
Oh, yes, yeah. Jupiter. Well, it's certainly comparable. It's certainly at least comparable. I mean, that one of the slight surprises, actually, of the dynamo models. I mean, when we were sort of pre-dynamo models, if you go back to the 1990s, yes, a lot of people thought that the toroidal field in the Earth's magnetic field would be much larger than the poloidal field. And then when people started doing dynamo models, most of the dynamo models produced things which had were more alpha squared rather than alpha omega. They were mostly had magnetic fields where the toroidal field was only comparable to the meridional field. And again, the Jupiter pictures, the Jupiter models tend to be similar. Now, that may be because RM is bigger actually in Jupiter, and a bigger RM is likely to produce a bigger toroidal magnetic field, of course. So I wouldn't put any money on it. I mean, it is definitely possible that there is a big toroidal field down there. But all I'm saying is that the models we currently have typically have a toroidal field of similar magnitude to the toroidal one. Yeah. Yeah. Yes. Yeah, that is true. Yes, that is true. Yes. Yeah.
From convection in this
Yes. Mm-hmm. The heat flux could be affected, yes. Yeah, yes, it probably would be. I mean, I'm sort of, in a very crude way, I'm sort of thinking of the spatial scale being this few thousand kilometers, so that you can convert the time scales in the velocity scales into time scales through that. I mean, that is quite crude. I mean, there has been some work recently, actually, on the basic fluid dynamics of how a shear, an oscillatory shear, would actually affect the heat flux coming through. So, I mean, and that's almost, it connects with experiments. I mean, you can actually sort of have convecting fluids and wobble them about and shear them and see how the heat flux is actually altered by that. And I mean, my take on that, on reading those papers, what I got out of them mostly is that if the velocities are comparable, then you actually get noticeable variations in the Nusselt number of the heat transport. So, yeah.
How you think about first. In reality, everything's going on. Everybody.
Yeah. Mm-hmm.
The way of thinking of it is like that large scale equation has the Lorentz first.
Yeah. Yes. Yeah. Well, yes, I think it is a reasonable way to proceed because of this. There's a big uncertainty exactly where the Reynolds stresses actually are. So there are advantages in keeping that element in it somewhat flexible. There are advantages in having that so that you can see what happens if the forcing is near the top and all due to the surface turbulence, or whether some of the ideas, what I call them Göttingen ideas, perhaps, that's what's happening deeper down. I mean, the thing is, of course, for these zonal flows, deeper down, the velocities are certainly smaller, but they would argue, well, the densities are larger. So maybe the actual momentum density down there is quite significant. And so these things are complicated. So as I said, so I think there are advantages in having a setup where you can actually look at different models. They're doing their thing, yes. Yeah. I mean, we do have information from these feral cells because they're related to the Reynolds stresses too. And people also have, I mean, Peter Reed and various people have looked at actually measurements of what the Reynolds stresses actually are, just by looking at the observations and trying to work it all out. You know, that's also that produces the right sort of numbers. I mean, that produces the sort of numbers that are comparable for doing this meridian circulation business.
What determines the depth at which the feral cell closes off?
Well, nobody knows what determines the depth at which the feral cell closes off. Basically, now, I mean, if you read that Juno et al. Paper, they say it might be 100 kilometers, it might be 3,000 kilometers. That suggests to me that they don't have a very good idea. Yeah. No, yeah, but what I'm saying is that even if it only goes down to 100 kilometers, if it sets that lateral temperature variation, yeah, that is providing the top boundary condition of the turbulent diffusion problem. Yeah. So I don't think it's necessary to explain all these things. I don't think it's necessary that the ferrule cells are necessarily deep. I think that meridional circulation might close off only 100 kilometers down, but it's still producing a temperature fluctuation, yeah, a horizontal temperature fluctuation of the order of a few degrees K. And that's really all you need, because then the thermal wind equation does the rest.